Hi everyone. Today we'll be discussing reverse coding, correlations, and simple linear regression. And we can get started right away. So I'm just going to open up my R Studio here. Oops. I'm going to clear my R Studio so that it is the update. And going to start a new project. We will put it session 2 project. Okay. So I've created a new project in a folder that I am okay with, and my global environment is empty, and I'm ready to start loading in my data and whatever R scripts I'll be using for today. So I'm going to import my data here. It's called A3 data. So I'm just looking up. Here we go. And again, it's asking us how we would like to import it. I take a look at my data frame. I am okay with the way that it's displayed. If you would like to play around a bit, you can see that it changes the way that you import it. And it's all based off of the way your data file looks initially. You might have to change the separator, but based on the way that my data file was created, I won't need to make any changes. And sometimes I do want to say you will get these like V1, V2, V3 for your columns. All you'll have to do is just put yes for your heading and that gets corrected. So basically, if you import your data file, you should always just take a look at it when it opens up to see everything looks good. All your entries are there. If this is looking odd, it might just be the way that you imported it. Not too much of an issue. So now I'm going to also import the R script that we will be using today. And the way that I did that was I pressed this little folder up at the top, and it brings me to the project that I've created today right here. And my R script is near that, so I can just put that as well. So what I learned recently is you can basically make this pop out of the tabs you were using it in. And I'm going to do that because I like having them separately. So just going to do this. Move some things around. Okay. And we'll just look at our data here. So we have 4 columns. First one is for the ID. It says it's an integer. Then we have self-esteem, narcissism, and antisocial. It tells us which columns they are as indicated by the little gray box that shows up in the range. But we can also see just a few examples right here in our global environment. And I have my console here. So again, every sort of feedback that pops up and any plots that we pull up will show up in this area over here. So I guess we're good to go. One thing I will change right now is, since I created this before, I put in a different data file, web directory. So I'm just going to change my directory by copying what was in my console and pasting it in there. I believe it didn't change very much. Yeah, it didn't. So I'm good to go. Just changing that in case if I ever, something happens to my data and I need to clean it up and start over, I could just press this broomstick and get rid of the data. And I could run this directory and it would bring it up for me right into my global environment. So don't have to go into the hassle of importing it, everything like that. And we'll just load the packages we'll be using today to get that out of the way so that we don't run into any problems telling us we don't have the package uploaded. So we'll just run those. Okay, so most of them are loaded now based off of the blue. It's in blue and there isn't an error or some sort of feedback right away. What I'm seeing from Psych is that some objects are masked by ggplot, and it says that the car package is also masked by, some of its packages are masked by Psych. I'm okay with those, I'll just have to specify when I'm using which package. For instance, down here, when I'm doing the correlation test, at the beginning, I just put Psych followed by 2 colons, and this just specifies to R, hey, pull this function from the Psych package. Hopefully, you have loaded all your packages now. And if you're getting some sort of different error, if it's weird or something's just not right, I suggest going right into your packages section and making sure you have you have that package installed into your R library. It might be the case that you can't load the package since you don't have it installed into your library.
So, Yika, what does it mean when you say the following object is masked by blah 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 package?
Okay, so what that basically means is some functions between these two packages are the same in their spelling. For instance, like core.test and core test are not core.test. Well, these two are not exactly the same. This one has 2 R's while this one has 1 R. But what it is that this one is from the base R package and this one's from the Psych package. But there are cases where we don't have that slight variation in the way that it's spelled. So you'll get 2 functions that are exactly written the same way, but are from 2 different packages. So R doesn't always know which package to use to run that code. And in that case, we would have to specify with something like putting the package and then followed by 2 colons and then that function, just so that R knows which package it's using for that function that is common between 2 packages. Does that make sense?
Yeah, yeah, it does. Thank you.
Sure. Okay, so hopefully everything is good now and we can get into correlations. So the first code I have here computes a variance covariance matrix, and it basically goes like it's using the actually I'm not sure if it's using the base R function, but you can find that out yourself. Hopefully you remember from the first session. Then it's followed by the data file, and then it's specifying which columns. So we've told R run the variance covariance matrix for columns 2 to 4. And let's see how that looks. So 2 ways it shows you can look at it. The first way is it just comes up in your R console. Right here, I have my variance covariance matrix in the diagonal, such as 0.367, 0.247, 0.1532. These are the variance scores for each test or each variable within itself. So how much variance exists in self-esteem, how much variance exists within narcissism, and how much variance exists within antisocialism. And then off the diagonal, such as these or these, and this one, correspond to covariance between two different variables. So how much two variables are varying with each other, not how much, sorry, in what direction. So from the positive signs, sorry, from the positive signs here and I think here, we can see that narcissism with self-esteem and narcissism with antisocialism, because they're both positive, they vary in a similar fashion together. So they both increase together or they both decrease together. And the parts where we find a negative, what that means is antisocialism and self-esteem, they vary in opposite directions. And if we ever find a 0, it just means that there's no relationship that can be predicted about their direction. And then I just wanted to quickly show you what you could also do is you could, if you're not using R Markdown, the good thing about R Markdown, what we saw last time, if I quickly make an R Markdown here, because I have R chunks, such as this, it gets really nice in that I can just insert the code, and when I run it, it shows in that section, you know, it won't get lost in my console, things like that. And I can even like make it pop out of my screen and have it on the side here. So that's the nice thing about doing it on Markdown, but you know, you might not always want to do that. And another way that you can look at your data to just make it nicer is if it's like a table, if it's like some sort of a matrix like this, you can create an object. I'm gonna call it covariance cov matrix, and you can specify that this is an object in your global environment as such here. And if I view this like that, it'll show up like this. So it's the exact same information that I have in my output, but now it's just not buried in all of this mess. It's just up here whenever I want to access it, or if I don't want to access it. So if now I guess we could move on. And I wanted to, before we get into actually doing the correlation tests, I wanted to show you some sort of, it's called correlograms. You could compute correlograms that show you a couple handy things. They not only show you the distribution of your data, but you could, in a way, use it to assess multicollinearity. And it shows you the scatter plots, it shows you the density plots. You can look at the range of your values, like the maximum and the minimum. It also gives you confidence intervals for those correlation coefficient. It gives you some correlation coefficients. And also gives you shaded areas that represent sign and magnitude of your correlation. So let's run one by one and I'll show you what I mean by that. So I wonder if I can make this pop out. Oh, perfect. So this here, you can adjust these if you'd like. So it says upper panel, panel .pts. I think it might be, I think this is what it is referring to. So this is the upper panel, I think, and then it says diagonal panel is the one that goes diagonally, and then lower panel is just right here. You know, depending on what your preference is, you know, you could use panel dot points, I think is what it says, to like the lower panel, but whatever you like, right? So up here we have a scatter plot. We can, nothing much else, but we can see that, you know, our data are good in terms of, you know, variance, co-varying with each other. You know, it's not like it's a dichotomous variable, things like that. You can just really quickly just like check a scatter plot. The distribution of your variable here, it appears approximately normal based off of that curve, you know, slight variations, but again, this is like sort of like a dirty and quick way of looking at where most of your data is, I guess, and the directionality. So this is sort of like the density that is kind of, imagine if your scatter plot was reduced to a circle, an oval, I guess, and a line. This is what that is kind of showing. So these two here, this one is this one, and this one is that one. And then we also have our other correlogram, which I find a bit more useful when it comes to correlations. So the line in the middle is just, you have your variable and it tells you the range of your values. So I just know in narcissism, they range from 1.4 to 4.21. That might not be as useful all the time, but here I have my correlations and I have the confidence interval for my correlations. So from your correlations and the confidence intervals, you can definitely say, oh, is this significant or not significant? And if it spans 0, so I know here, because it does span 0, I suspect that antisocial and narcissism are not going to be significantly correlated with each other. And then antisocial and self-esteem are, and so are narcissism and self-esteem. So what I meant by you could check multicollinearity is, say you were doing multiple regression, which we won't be covering today, but if you had a multiple regression and you want to see all of these things kind of predicting another variable, let's say happiness, or let's say extroversion, you wanted to see if all these three are displaying any multicolor linearity with another variable called extroversion. You would basically check to see, hopefully they are all correlated. The correlations with happiness would show up in this extroversion would show up in this fourth column here. And hopefully they're correlated with extroversion such that they are significant predictors of um, um, extroversion. But you also want to see if there are any correlations within your predictors, and you might see that, you know, you should be wary of self-esteem since there are correlations within if we had a multiple regression. But right now. So we're just gonna close
Can
this.
we tell the p-values of the, I know this is only like a very brief
Mhm.
overview of the correlation values, like of the R. I'm just wondering, does this graph show us at all about the p-values for each?
So that's the downside to using the parallelogram. You won't get the p-values. Yeah, you can just say, oh, significant or not significant. But we can look at a correlation matrix, and that one will give you a p-value. So, and then, okay, so sorry, I'm gonna show you the correlation matrix you can create with the base R first, and then with psych, just to show you the difference. So this is creating it with the base R. So these are the same values as we had before. I'm gonna make this into a table so we can look at it from here. So these are, these are the same, yeah, same values as what we get in the correlation correlogram, but because we're using the basic base R package, we don't get the significance values of these correlations. We just see what they are. That's why people don't typically use um, just the matrix from the base R. What you can do if you want to continue using the base R function, there is a different separate significance test that you could do using the R functions. And basically, I would say the upside to doing it this way is you're again zoning in on one specific uh, bivariate correlation, as opposed to creating a large matrix with a large amounts of variables. Let's say you had like 20 variables and you're comparing them with like 20 others, right? Or something like that. That would be a large matrix to look at and a larger uh, significance matrix to look at as well. So here, using the base R functions, you can get a whoops, that was the covariate. There we go. You could get a you could get the correlation matrix, but you can also get the separate significance test running this function here. And this is how it shows up as. So I'll just look at this here. Yeah, so this is what it shows up in my output. Tells me the title is Pearson's product moment correlation. So it's giving us the Pearson correlation coefficient, which is down here at the bottom. So 0.39, 0.439. So we're looking at the correlation between narcissism and self-esteem as shown in our code, and also corroborated with the plot that we had before. Shows us the test statistic, the degrees of freedom, the p-value here, and what the terms are for this test, such as the alternative hypothesis and also the confidence interval. So a bit more information that can be useful. But again, this is typically not my favorite way of running the correlations, because I think another, I guess, more comprehensive method is using the psych package, because the correlation tests that exist in the psych package, you could easily suggest only one correlation if you'd like, I believe. And but you can add more to it. You could do more things. For instance, that you might not always want to get a Pearson correlation coefficient, so you can always change this to Spearman or Kendall, depending on your data and what kind of tests you're trying to run. You could also make adjustments if you'd like by indicating for the just for like the multiple comparisons, adjusting for any kind of p-values. If you have a large sample, um, things like that, you could determine which type of test you want to do based on these. Or if you don't want to do any, you can remove it, and you can change the alpha. I'm sure you can change the alpha for that too, but I think the benefit here is you get this. You get not only a matrix, but you also get a p-value, and you're able to do adjustments and change the type of the correlation. And in the case if you just want very simple, um, you don't want to indicate correlation, bivariate correlation, Pearson's, or if you just indicate it like this would be identical to having this as none. Just for your information, so this is like the default version. Basically what I'm trying to say is the default version without indicating anything else will run your correlation test using the Pearson's R, no adjustments, and using the alpha of 0.05. So if I run this, how this comes out is like this. And it tells me the top correlation matrix here. What I see is the correlation coefficients, the Pearson correlation coefficients among my variables. And then at the bottom here, what I see is the p-values, and I can see, as suggested by our correlogram, antisocial and narcissism are not significantly correlated. And it seems like there weren't any adjustments to be made for, there weren't like, there weren't many the adjustments didn't show up. I guess it didn't um, apply in this case. So the adjustment that I used, the home adjustment, if there was an adjustment to be made and make a difference in the p-values, it would have showed up in the entries that are above the diagonal, so in this upper region, and these would be different from the ones in the lower region. But in this case, with the data that we have, it seems like you don't necessarily need to do those adjustments. That's why it just shows up as 0. So what I like to do is I like to indicate the adjustment, because I get the values for the non-adjusted at the bottom here, and I would get the values for the adjusted at the top here, within the upper panel versus the lower panel. And then the last thing I want to show you is how to, this is, in my opinion, this is one of the best things you could do with R, since it gives us an APA style table. And this is one of the other very comprehensive ways of doing the correlation tests, because computing the APA correlation table, what it will give you is, well, let's see. So basically what I've done here is I've not only created a output file labeled as table1.doc, so it's a Word document, and I've indicated the table number within that document previously by putting 1, and I've also told R which columns to use to get this make this table, but I've also made it into an object in my environment, because if I just look it up here, it'll give me some information about the table. This might not necessarily be useful all the time, but I yeah, I don't find it totally useful. I yeah. Um yeah, you just get some information that, in my opinion, is just kind of about the variables that you're using. But because so I've created a folder, a document, but for time for the big reveal, let's see how it looks. And actually, there we go. So if you actually created a project, it doesn't save somewhere random. It saves in the folder that you've created for your project. So it shows up in that section. But if you have a Mac and you didn't create a project, you could search up the name. Hopefully it comes up for you. But because I did create a project, this is just more handy. So I'm going to press this and see what it looks like. Maybe I'll extend this a bit. Okay, so, and you can also edit this right into the table, in the table as well. So it creates sort of like a pre-made APA table for you. It's great. It gives you the mean and the standard deviation, something that we didn't see in the previous um, tests. And you also get a matrix, and you also know the significance level here. And you also know the confidence interval of each of these things. And, like, it copies your variable names right from your global environment. So say if I don't want that dot, I would just have to go back and fix up a couple things, if I want to, if I want to adjust some things. But this is just great. It saves you time if you are uh, going to be making any tables, things like that. So if there aren't any questions about bivariate correlations, we can move on to the simple linear regression section.
Sorry, I have one question. So for R, other than aside from correlation analysis, is it also able to provide us with tables from other analysis, like a regression table or just like or a chi-square um, table, just any other
So
table?
you're talking about APA tables, right?
Yeah.
Okay, I believe so. I end up showing an example with the simple linear regression stuff.
Oh, I think I see it. Sorry if you, yeah, APA table
um,
yeah, okay, perfect.
there are other types of tables you can make too. Sadly, like, it's not always, it might not have everything, but I feel like it has most things.
Yeah,
So let's take a look. So I went in my packages, I see APA tables. Um and I want to see the type of functions that exist within um, APA tables. So it seems like I can make a one-way ANOVA um, table. So this gives me a table of means and standard deviations for one-way ANOVA, two-way ANOVA, creates a fixed effects ANOVA table. I'm not sure what that is. Correlation. So this is the function that we're using.
yeah.
Yeah. And then D values for all paired comparisons in APA style. Um, base output of easy and some of these things I don't even know what they are. This is a bootstrapped regression table with
Bootstrap confidence intervals, yeah.
regression table. This is the one that we use later.
Okay.
This is just the label of the package in general.
Yeah.
Um, I think-
It's okay, Yekta. I'm just curious. We can move forward. I can look through them, so I don't want to take up everybody's time. I appreciate it.
okay. But yeah, for the most part, it can do when it does do when it does create tables, they're nice.
Yeah, for sure.
And then any other questions for this section? Correlations? No? Okay. So yeah, as I mentioned in the email, you can definitely do partial and semi-partial correlations. And actually I'm familiar with this data, and we see that the antisocial, and I think it was antisocial, and which one was it? That was not significant. Antisocial and narcissism, they're not significant here, but actually it was either after the partial or semi-partial correlation that you do actually end up seeing significance after you run those functions. So those are some things to keep in mind that you are also able to do in R. I don't know if we'll get time to cover them today, but if it's something that you guys want us to cover, I'm okay to cover that next time as well. So in simple linear regressions, uh, how I suggest going about it is first creating your model, and then you can go about checking the assumptions and distributions, things like that. And I would suggest the same with multiple linear regressions as well, just because it's better to figure out what you want to include in your multiple linear regression first, whether you want to use like a hierarchical method where you put things in based on, past literature and what you want to have authority over what you want to go into your uh, model, or whether you want to do stepwise, backward, forward, hybrid. First determining basically what goes into your model, and then looking at the assumptions, just because you need the model first. So here we are regressing antisocial behavior on self-esteem. That's what this line of code is referring to. So basically I'm creating an object in my global environment called lm.1, and it's formed from a linear model. That's what LM means. And the linear model, as I said, has antisocial. This is regressed on self-esteem. If I had more variables, I could actually go in and put them in right away. If I wanted to include an interaction, I could use the asterisk sign, but I'm getting ahead of myself. So, and the last thing you need to indicate is where this data is coming from. And as I've said before, since I have indicated where the data is coming from, you can see that I didn't have to, use this dollar sign to indicate where each of these variables are coming from, as we would in some other lines of code, just because we end up determining that later. So if I create this in my environment, this is how it shows up as. This is all the information, a bunch of stuff that barely makes sense. Um, but that's not informative. So basically, I need to see the summary of my linear model. So once I run the summary, and what we see here is we get the summary of the model with the model parameters. Whoops, I have a typo. Parameters. I get my p-values associated with my parameters, and I get the p-value for the model is down here. And I get the r-squared value, and as well as the adjusted r-squared value for the model, and standard of error, and this is my slope here. And as where is it? So this is self-esteem regressed on antisocial. So there we go. What am I looking for? Okay, maybe I don't remember what it was. Sorry, I'm talking to myself. Yeah, so based off of the asterisks, you can see the level of significance. That's what this stuff down here is indicating. It's giving us some information about the residuals here. So the minimum, these are just like the quartile ranges, interquartile ranges, yes. But the most important thing we're concerned with is this part right here. The only thing is the slope that we have here, because we're doing a simple linear regression, our slope is not, we want to ask like, what's the effect size, right? With correlations, very easily you can use the correlation coefficient itself as a measure of effect size. But in regression, like, what do you use as the effect size? Because the slope that we have here is associated with the units of the study. So how do we find a measure that is standardized across other studies and can be comparable in other ways than effect size? And what you could do is, we would just call this b for the slope, like little b, and we can calculate the beta using this function here. It's using the quantpsych package. Hopefully I have it. I don't, I think. And we can see that, oh, I think I do have it loaded because it worked for me. I wonder if that runs for you. But basically what this function did is it obtained the beta for self-esteem, and it standardized our slope from this statistic to this statistic. And again, if I was doing a multiple linear regression and I had more slopes, if I had more estimates here of the slope, then it would just show up as a new column. It would say like, let's say if we did narcissism, right? Since that's not in our model, if we just added narcissism, it would just show up here, and the beta associated with that would just show up. So now that we've done that, let's look at another table, another APA table.
But before you move on, I'm just a little confused here. So you're saying that to look at the effect size for the predictor, you would do the quant psych formula.
Yes.
But wouldn't you look at the R square?
Yes, you could look at the R squared for like the model fit, I would say, like, just to see how good your model is representing your data, I would say. But if you're specifically focused on that predictor itself, and if you're trying to compare it across studies, for instance, I think using the beta, the standardized slope of that predictor, uh, it's a um, it's a good way to look at the effect size of like that slope across studies.
Oh,
And
okay. Okay,
this
whereas the R square speaks more to the overall model, just in case we have multiple predictors, and the quant psych formula, it points more specifically to each predictor.
exactly. Yeah.
Okay.
Yeah. So okay. If there are no other questions, let's look at another APA table. I always get excited about running these. So it shows up in my it shows up in my console, gives me like a rough way of looking at it, but we want to look at the nice way and see what our table has here. So, you might not use everything that's listed on here, um, but here, there we go. So in a simple what I was looking for before, where where I was talking to myself, I was looking at the model to see if there are any sort of similarities between my linear regression and the bivariate correlation. Because since we're doing a simple linear regression, it's very much the same as a bivariate correlation between those two variables. So I was looking to see, what was the same within these two things. But the slope that I obtain here that is not standardized is not the same as the correlation coefficient, the Pearson correlation coefficient, but the beta that is standardized that I obtained here after I standardized my slope is the same as the Pearson correlation coefficient, because we're doing a simple linear regression. Because if we were doing multiple linear regressions, the Pearson correlation that would show up would be more comparable to partial correlations, since we would be controlling for other variables that are in the model. That's what that R would show. But that's not relevant here. I don't mean to confuse anyone. But basically what shows up in our table is we have the predictor. Again, if you want to change this, you can go back later and change that. We have the intercept. We have the significance of the slopes. We have the confidence interval of those slopes. We have the standardized betas. So, if you compute the table right away, you don't have to go back and do this. But again, you might not always want to create a whole table just to look at one statistic. So that still comes in handy. And then confidence interval for the beta. The SR squared represents the semi-partial correlation squared. I'm not sure how much I can say about that statistic. I know the semi-partial correlation itself is looking at the correlation between two variables when you control for another variable in one of those variables you're comparing. But I'm not sure what it tells us when it's squared. So I can't say much about that. But it seems like it's not significant. Seems like you can have significance associated with the semi-partial correlation squared. And then we have the R here, and it represents the zero order correlation, which is the Pearson correlation. And then we have the these are just the LL and UL represent the lower and upper limits of a confidence interval. Finally, we have the fit of the model listed as the R squared. It's not the R squared adjusted, because we have the r squared adjusted here and the regular r squared there, and we see that that's the one that it is referring to. And if you just multiply this by 100%, you get 14.3. So you know your model, uh, it explains 14% of the variance that exists in the data. Basically, in this case, we only have self-esteem. So self-esteem explains 14.3% of the variance in the data when antisocial, I think, when antisocial is regressed on self-esteem.
Yigta, I'm wondering how would we be able to enter like multiple predictors into the equation, like
So
into the model?
in doing like a multiple linear regression,
Yeah, like for instance, we would regress antisocial on, oh, I forgot what the three variables are.
self narcissism.
Yeah, on self-esteem and narcissism.
So I think we'll have time to do that since like the reverse coding stuff won't take very long. So I think after I'm done with the rest of the stuff here, I'll show examples of the linear, a multiple linear regression
Okay.
uh, in the end, if you remain patient enough. Very eager. I like you, Doris, as a student. Um, sounds good.
Yeah, sounds good. Thank you.
Okay. So if there's no other questions about the stuff here, I'm just going to close that. Here's the thing, like, say if some of this information is unnecessary to you, you know, you don't always want to have the confidence intervals, you can always delete columns. The good thing is, you know, you already have a pre-made table that you can just edit and add to. So that's always helpful. So I'm not gonna save this. And then now that we have a model, let's just check it out and see what the residuals look like, because we would like it to follow one of the assumptions of regression is that the residuals follow a normal pattern. So we can run a ggplot, and this would be a histogram, and here it's telling the bin width, the color, um, and then it's using just the count. So and these are just, I think this is just the color again, and it's also running a function that adds a line to the histogram, and this is a normality line. So and it'll be in red. I'm trying to basically read the code and predict what it'll be before beginning, and we will see now. So uh, we can see that the data that it's using, it's not our data file. It's not that our data frame, that it's not coming from our data frame that we have up here. It's coming from the linear model that we created, that object in our global environment. But it is using, and it's using the residuals from that object. So the cool thing is, as when we created the linear model, you know, it has all this information here and more. It's just embedded within the linear model. It's just a, so there's information on the residuals, right? There is 1 to 250 numeric observations for every single residual, because that's how it computed, you know, the standard error, the estimates, p values, all those sorts of things. So it has every individual deviation. If you remember what residuals are, it has every deviation from one of the observations to the model as suggested here. So, and that's labeled under residuals as shown in the gray box. So we can take advantage of that um, item within the object called lm.1 that we've created. And that's what we're doing here. We're using something called residuals that was made that is within lm.1, the same way that we use our other variables here where we pulled information from self-esteem, but from the data frame A3 data. That's sort of how we will be computing the um, plots. So I think, oh, whoops, it's this one. So I think that's a really cool way that we can compute it, because running the model also creates the residuals. It creates the fitted values, um, a bunch of stuff. So that's cool. um, Now we can run this and zoom. So this is what it comes out as. And we saw that the bin width was 0.25. Um, uh, I think this is correct. 0.25. I think these are point. No, that's not. I don't know if they are 2.5. Not sure if this is for the X or for the Y, but changing this will certainly change how it looks. I'm kind of curious. Let's see how this one looks if we change the bin width. Yeah, so it's just for bottom. Yeah. Okay. So this looks nicer. Basically, it plotted the residuals, and the residuals look very close to that linear line. So this should also be seen if we run a QQ plot. So again, it's pulling this information from this data. This is where the data is coming from, the linear model, and also it's using the residuals to create the QQ plot. And this is what it looks like. So we can see that majority of the observations are clustered in the center, which is good, and it's in the middle of the linearity line. There aren't crazy curvatures, so we know that it's good that it's on a linear model and that there aren't any curvilinear sort of relationships going on, and not many far deviations from the linear, the uh, line here, the line. I forgot the name. So that just shows us that there aren't crazy outliers. So it seems like the QQ plot looks quite all right as well. So we can also look at the predicted and observed values. What that basically means is, every individual every individual dot here, this is the scatter plot that we saw before in the parallelogram and all those things. Now it's just, I guess, nicer, and it has the predict, you can see where the predicted and observed values are, such that every individual point is corresponding to a single observation. So those are the observed values, and this line here is our model, our simple linear model, and I believe that this is the range for the confidence in, like, the 95% confidence interval. I believe so. And you're able to see, like, the range, I guess, in which the observed values fit within that region. And then the last thing, we can look at the plot of the residuals. So kind of if you're looking to assess homoscedasticity or variance within your residuals, you want to see that, there isn't like a weird pattern going on. Again, that there is the variance is pretty okay throughout various levels, at various, I guess, at lower and higher values of our predictor. So that looks pretty okay as well to me. There isn't like a weird curvature here, or some kind of U, or upside down inverted U pattern going on. So that looks pretty random and all right to me as well. Um, yeah, so those are some of the things that we can do with simple linear regression. Now before we get to multiple linear regressions, we can look at the reverse coding. To do this, since I didn't have like a data file that I could use that has, say, like, let's say it had like Likert scale data, uh, I'm going to just create a data frame. The way you can make a data frame is as such here. So what I've done is I am going to create an object that is actually going to become a data frame. And so survey will be the name of the data frame, the same way that A3 data is the name of all of this data. Sorry. And it will contain two columns of participant number and age. So let's run this. And here it is. I am going to now open this up and just see how it looks. I'm going to keep this open for a bit as we end up adding more and less information here, just to see how things change throughout every time I run new code. So what I've done here is I've indicated a column by using the double quotations. It knows it's the name of a column that is binding 1, 2, 3, 4, and 5 as such. And the order here is very important. So if you're manually entering in data, you want to make sure that participant number 1 is matched with the right age, since they will correspond to each other. Same thing with this. Now, let's say I want to add a new column of my participant sex, and I'm indicating it using M and F. I've put them in double quotations because double quotations indicates a character, while no quotations here indicates a numeric data versus a character string, basically categorical data. Yeah, so now I have that. Another thing I want to add is condition, but again, I'm just making sure that they're entered in the right order. So say, like, participant 1 is male who is 24 years old, who is in the control condition. That's what I have so far. Now, let's say if I want to change the name of one of my columns, I would basically put names. I would put the data file that I am making changes to, which is, we called it survey. And I would indicate the column that I'm looking to change. And if you're not sure of the column, as I've indicated before, if you just hover your cursor on that column, you know, let's say you have a bunch of columns you don't know, you don't want to count from the beginning, right? If you just hover over it, it will tell you which number it is. If I run that, we can see that it changes in the data. Now, a couple things are very important before you start running your data. And, you know, we've been lucky so far with all the data files that we've imported into our global environment this session and the last session, such that, you know, they were all numeric, and we didn't have any problems with them. We didn't have to change anything. But you might come across the case where even after you've imported a data file that you've created yourself or a data file that someone sent to you, you're trying to run a function and it's just not coming out right. It's saying weird things. It might be telling you that, you know, it might say like sex is not a factor. And say like if I was trying to use sex in an ANOVA, or if I was trying to use it in a logistic regression, which you can do in R, by the way, um, uh, because it's just labeled as a character, then I'm not able to compute uh, my, I'm not able to compute that output. So it's very important to make sure that everything that you have there is in the right class. So the class for age is numeric, the class for sex is character strings right now. But say we want to change sex into a factor and we want to change the labels from M and F to 1 and 2, we want to recode them. This is how we would do it. So if we look, this has changed in our data file, and this has changed as well. So now R knows that sex is a factor with 2 levels. For further analyses, you won't come across that issue. Now I've indicated 1 and 2 for male and female just because, you know, 0 doesn't have a significant meaning in this case. But in the case if I'm doing like a condition, 0 would have a significant meaning. And this would also be very important when you're running like logistic regressions as well. So I want to recode it and make sure it's just 0 and 1. If I run that, again, I see that it's become different in here and in here as well. It says now that it's a factor, that condition is a factor with 2 levels. Now, let's say that I had a question 1 of my survey. I have a Likert scale that goes up to 4. I don't know if that's a thing, but let's just pretend, you know, it might be the case that it's 5, 6, or 7. You can always change it up and add to it. So let's just add it in. So that's my question 1 and all the responses that I've gotten for that question. You know, 1 could suggest maybe like strongly agree. 2 might be agree. 3 might be, well, that would make it 5, but you get the point. Yeah, so they just correspond to some sort of a agreement or whatever you are testing. It might be how they feel towards it, whatever it may be. What I'm trying to show here is that when I have added this column, they showed up as numbers. Sorry, it showed up as a numeric data. But if I wanted to add categorical data into my data frame, it would be really important that all of these things are in quotations, because it tells R that it is the name itself is meaningful. When you don't use quotations, you're telling R that the numbers are meaningful. So in this case, it's showing up as character strings because the name is meaningful, such that this could be relating to numbers of hockey players. Who's your favorite hockey player? Number one, number two, number four. That's its named as categorical. But that's not what I'm interested in. I don't want to deal with categorical variables. So I'm going to be changing what I had in there to make it numeric. And the way I did that is I just removed the quotations. You can see nothing changed in my column, but it changed in my global environment from character to
Sorry, I got so if the values are categorical in nature, then we just have to put quotation marks.
exactly. And it's also suggested here as well. Whenever you see double quotations, you can suspect or you can expect some sort of a label, some sort of thing that has a valuable name.
So if we are to import a data set into R and then one of the variables is categorical in nature, then we have to manually tell R um, to perceive that as such, right? By putting quotation marks. Because I don't know if R would automatically recognize like what variables are categorical, which variables are continuous.
Mhm.
So do we have to manually type in this command, like the quotation marks?
Mhm. Good question. That's a really good question. I think R, for the most part, tries it can be very smart, and often it recognizes those things, especially if you have like actual words. For example, if you import a file that says like, experimental, conditional, these sorts of things, it'll be very smart and it'll know that it's a character. And you should look at the information. So just pressing down, like, for instance, let's say survey was the file that you imported, just pressing on that arrow and checking it out. If you're curious and you want to just double check and make sure, you could check by seeing if it says numeric or not. Another way that you can check is if you run, um, if you put an str and then you put the name of your data file. So I'll put survey. And right now my questionnaire 2 is numeric. So I'm gonna check how that looks. This is how it shows up as. Um, in this case, I don't have that many observations and I'm able to see them all. But as we saw in here, there's those extra observations that I'm not able to see. And if you run this R code here, you'll see every single one. It gives you a full information on your output, and it tells you the class of each individual variable that you have indicated in your data file. But now I just want to see like what happens when I change it to a character string here, and I want to see how that differs, and it shows up here. So what I would recommend is checking if R was smart enough to have uh, basically recognized that. And if it did, then great. Like you don't have to make any differences. But if it didn't, there might be the case where you might have to.
Okay, and then when I download a data set from Qualtrics, which format should I download it as? That's the easiest to get into R.
I think that depends on some things. If you're importing from it depends on here, I'll show you an example. Okay, so depends on the extension. So the file that we imported, the A3 data file, it says that it's a CSV file.
Oh, okay, got it.
So CSV files, you can leave the separator as a comma and it shows up nicely.
Okay.
But you might have the case where like I'm trying to see if I have any other like data files that might not be CSV files.
Do you
For
have
instance,
any SPSS data files?
let's check. So for instance, like this one was a .dat file, and so a couple of things are wrong with this. The headings are not correct, so I have to fix the headings like this, and then I have to fix this. The separator is on tab. For the CSV, we had comma, and if I have comma for this one, it'll show up like this, which is incorrect, and I'd have to put a tab to correct it. What other files that I might have? Let's see. Oops.
I'm just curious. What if we and we don't have to do this right now. Like I could import a SPS data file and see what it looks like. I'm just curious.
I have a text one. I don't think I have a SPSS data file. If you want, you could send it to me. I can try to import it.
It's okay, Yekta. We can move forward. I can yeah, I can play around with it on my own. It's fine.
Also try to do maybe a Google search. Like you might just be able to just say from SPSS. If you go
Yeah.
like that, this might work. Not sure.
Okay.
Try and see. It's dependent on the separator is what's important.
Right.
Okay, so now let's say now that I've changed my question to numeric, let's say I want to reverse that question, but I might not want to reverse the item itself. For instance, if I just went question 2, recode that question, 1 becomes 4, 2 becomes 3, 3 becomes 2, 4 becomes 1. If I make this change, it changes my data, completely changes the entirety of the data that I had initially. And what if I forget? What if I forget what these numbers mean? What if I forget if I even reversed this question? So I'm going to put my data file back the way it used to be. But instead of changing that data and rewriting it, essentially is what I did. I rewrote the data. I would just make a new column and label it differently such that in the survey file, we are creating a new column called q2.r, suggesting reversed. But what it is doing is using information from the question 2 and changing the items as such. And it gives me a new column. So this way I don't change the data that I had. I just create a new column with the reversed scores. Does that help with everything that we were going to cover this week? If there's
Yes.
any,
Yes,
okay.
you've done over and beyond. Thank you, Yekta.
Can I ask a question, Yakita?
Sure.
So I'm just wondering the difference between, you know, just like what you did, you kind of transform the data format from character to numerical, but you also did a demonstration of factor, which, you know, you put those like numbers under quotation mark to kind of numericals to me, you know. So I'm just wondering if you can compare these two transformations, like why you sometimes could directly, or like what conditions you would directly transform the character to numerical, and when will you do this factor? Do you understand my question?
For sure, yes.
Yeah.
When we are changing, let's say sex, for instance, sex initially, we had it as a character string. The data was not numeric, it was just characters because it was just M and F. When I changed, what this is doing, it's changing just this part of the code. It's changing M and F to 1 and 2. But 1 and 2 are remaining as character strings within their, like, R still recognizes that what has changed is just the M and the F. It hasn't changed from a character string to a numeric data. But so that's what this part means. But here, that's where these two are different. So we rewrote data that was characters and we wrote it into numeric data. So doing this part doesn't change that aspect of the data. Another thing it introduces is making it into a factor. So telling R that you can separate the data, all of the data, the 1 to 5, all participants, by a factor called sex, such that, you know, that sex will only ever have 2 levels of 1 and 2, which is just a label for what it actually is, and that is M and F. So having it as a factor tells R that it can vary to 2 levels only. And once R knows that it's a factor that varies at 2 levels, if we do a one-way ANOVA, or if we do t-tests, having that is important, and it's relevant to being able to run those sorts of tests. If R doesn't recognize something as a factor, it might not run those sorts of tests. It might be like sex is a character, and it won't be able to use data that's just characters to run that ANOVA. It would have to know that it's a character that is part of a factor that has 2 levels, basically. And once it knows that it's a factor, it's okay that it's a character now. Does that make sense?
Yeah, I think it makes more sense to me right now. Thank you, Yakita.
For
And
sure.
factors don't have to be limited to like 2 levels, right?
Oh, of course not. So if I had more things in here, I could definitely like add a lot more if I want. Yeah. So it's kind of just in terms of, you know, it makes sense to us in our head that, oh, of course, sex is a factor, male and female, you know, in our head it makes sense. But R doesn't know that. So we have to tell it because, yeah, it won't be able to compute those sorts of tests if it isn't stated that it's a factor. In that way, R isn't the smartest. Okay, so since we have some time, we can look at the multiple regressions that we asked about, but I am just going to change some things. For instance, I'm going to change the name of my linear model. I don't want to overwrite what I already had, so I'm going to call it LM2, linear model 2. It's actually the same, it uses the same code actually. The only thing is we would just have to add narcissism, the way that it's spelled. Yeah. So for instance, like, let me show you what happens if I put narcissism with a capital narcissism. If I wrote it as in this way, if I wrote narcissism in this way, this is what happens. So it gives me an error, and it further explains and says object narcissism not found. And that's because of the casing. It has to be lowercase. And say if I had included a different data file, so for instance, like we tend to copy code that we've borrowed from other templates, and it might not always have used the same data file, and you might have just forgotten to change the data name to match the new one, and it says object antisocial not found. You might be really confused. You might be like, but it's right here and it's right here. That might just be because you forgot to change this part of your code. And again, if this is an uppercase D, it won't compute it. So if you're getting errors and you're getting really frustrated, I suggest just going like one thing at a time, like making sure, okay, this is good, whatever. And then when you get to just reading it one by one and making sure that everything in there looks good. So I'm going to run this. And now it's worked. Now I don't get an error. And I'm going to get the summary for the second linear model. And this is how it shows up. I'm just going to copy these down here. Okay. So a couple of things that are different is what we see. Okay, here we go. So now we have narcissism added, and as opposed to, what I'll do is I will also run the summary of the first linear model so that we have them right side by side. So this was self-esteem in the simple linear regression, and this is self-esteem now when narcissism is controlled for. So actually the slope increased when narcissism was controlled for, as opposed to when we had a bivariate correlation or just a simple linear regression between self-esteem and antisocial. And when you have only two predictors, you can also make those sorts of predictions about partial correlations or semi-partial correlations. You can tell that when narcissism is controlled for, self-esteem has a greater correlation with antisocial behavior, because we see that increase in its slope, and that increase in its slope would also translate to an increase in its correlation coefficient. And that just means that there was a suppressing relationship that existed between them. It might be the case that this was lower when we included narcissism, and that would just mean that there was an inflated that narcissism that when narcissism isn't controlled for, that we were getting an inflated score that wasn't representative of just the relationship between self-esteem and antisocial behavior. So other things is now we get a p-value that's also associated with narcissism. Now we get, again, we have the multiple r squared, and we also have the adjusted r squared. Some things that I would just mention is, as we end up adding more predictors, the model tries to, in a way, penalize the model for the increase in predictors. Because of course, if I had like 20 predictors in my model, I could have an r squared that's like 80% of the data can be explained. Oh wow, what an amazing model. But that's like 10, 15 predictors, right? So what the adjusted r squared does, it tries to penalize the addition of new predictors such that it adjusts for that increase you see anytime you add a new predictor. You know, we want that adjustment not to be due to the fact that we just have as many predictors as possible, but because we have good predictors, not predictors that aren't significant. Because here's the thing, if narcissism was not a significant predictor, we would still have an r squared that is more than what it was without narcissism. That adjusted r squared, though, would be closer to what you would see if it was just self-esteem. So when you start to add more predictors, it would be better if you looked at the adjusted r squared instead of just the regular r squared statistic. And now we just also have the p-value for the overall model. Now let's see if we can run the betas here. So what we see here is the, so we see the standardized betas for our slopes. And another thing we'll do is we will get the APA table and go into files, is in here, and we can just compare it with this previous one. So as in my R code, I changed the name of my table from table 2 to 3. That's been noted. But I will show some things here. So as you can see, the R is the same because these are just the zero order correlations. But other things are different, like the slopes and the betas that correspond to those slopes. Also the partial correlations. I suspect that these are due to that controlling effect, such that now self-esteem is predicting antisocial behavior when narcissism is controlled for, and narcissism is predicting antisocial behavior when self-esteem is predicted for. I suspect that this is what that's referring to, and that's why you see that increase from 0.14 to 0.21. Again, I don't totally know what the squared means, but that's sort of just my suspicion of what it's suggesting based off of my knowledge of what a semi-partial correlation is. And then also we just have that R squared value. We don't have the adjusted R squared in the table, but again, you can always just change that, make this adjusted, and then, make the changes right in there. Those are all based on your preference. Then I wonder what this will look like if we changed these as well. So I just have to go in there and make sure that every instance of LM1 is changed to LM2. And I'm just going to do this since I might not notice everything, but I'll be cautious to press replace all, because in this data file, I don't want to mix up things that I had before in the simple linear regression section. So I'm just going to go individually one by one, and that will just help me be more careful. So now I know to stop. And then we can run the plot for the residuals. The QQ plot. Yeah, as you can see, like these the histogram didn't look quite as different, but now you can see that there is a difference from the QQ plot compared to the first one that we saw. It seems like there is a larger deviance in some observations that may look like outliers. Well, that's just because, we're including more things in the data now. And then that's just plot of the predicted and observed values based off of the new regression line that we have computed. And let's see what this looks like. Looks at that. Now, there are other things that you could also look at when it comes to multiple linear regressions. And since we have a few minutes left, I'm just going to see what other things I can show you. So as we suggested before, the data, you can always run the correlogram regardless, but you might want to do some new things for the model since now we have more than one predictor. Not sure if we will. I'll just paste it in there if we have time. Okay. Okay. All right, so a couple things that are that we can do now that we couldn't do with a simple linear regression. So as you can see, these are our code that were created using a different data file. So I just have to make sure I'm changing things as I'm going along. The first one is just my linear model, as we've multiple linear model as we've created it before. But now we can check some things. I don't need to run this again since I already have it, but I just did it anyways. What we can check is if there are any independent errors. And what this gives us is actually it gives us the, Darwin, what was it called? Darwin Watson? Derby Watson? I can't remember the exact name. I think it's called, we can find out actually, DWT. Let's see if I can find it in help. DWT. There we go. Durbin-Watson test. So this is the Durbin-Watson test, and it is looking at autocorrelations and independent errors, making sure that there aren't anything like that. For very important for multiple linear regressions if you're checking your assumptions, and it just does the test as it would if it was like a like similar to the Shapiro-Wilk test. It gives you the test statistic and the p-value. So what we are hoping to see is that it is not significant, because if it is significant, it would tell us that there are independent errors. And because it is not significant, we can confidently say that that assumption has been met. So another thing that we could do is checking the, as we already have checked the homoscedasticity, linearity, and normally distributed errors with these things here. There's a different way you could also do that. That might be a lot quicker. If you just run the plot and the linear model. If you oops. Okay, actually, let's rerun that. So basically how it shows up is like, oops. When you run the plot of the model, it gives you basically all of the plots that we looked at. And the way that if you are running it in your R script and in your console, you would need to press the return key to see the next plot. So this is the first plot. It's a QQ plot. When I press return, it shows me the next plot. This is the plot of the fitted residuals. And then if I press the return key, it gives me the plot of the leverage and the residuals. And what we are curious about here is making sure that there aren't too many observations too far to the right and too far down from the x-axis. Otherwise, I would suggest an outlier or an influential case, yes. And then if I just press the return key again, I think that's all actually. I think those are the three plots that it gives me. It gives me a plot of the fitted residuals, the QQ plot, and the leverage. Okay. So we've already ran the summary and we've already looked at the standardized coefficients, so I will get rid of this. One thing I wanted to mention is with multiple regressions, we determined what we wanted to keep in our model. We determined that we wanted our model to be antisocial, regressed on self-esteem and narcissism. We determined that ourselves. But what if we were looking to have a software controlled method of creating a model such that it's not us determining what the model should be, but the computer determining what the model should be based on which model would create the best fit. So that's sort of like following a stepwise regression method of determining what the model should be. There are a couple ways you can do that. There's the forward method, there is the backward method, and there's also where is it? There's also a hybrid method where it does both, where it begins with a forward stepwise regression, but also does a backward stepwise regression each time it adds and removes a new predictor. So it kind of does both. If we do,
Sorry, I'm wondering if we should save the multiple regression for next week. Yeah, I'm just mindful of the time, and it looks like there's a lot to go through, and I don't want you to rush through it. So I'm just wondering if that is okay with everyone.
yeah, we only have a few minutes. I don't think I could.
Yeah. So we kind of stop at the introduction to multiple linear regression, and that could be our main topic for next Sunday, if that is okay with everyone. And hopefully that will give us a refresher of the regression analysis that Yekta did for us today in R.
Mhm. Is there any questions, by the way? If anyone has any questions from everything that we've discussed today? No? Okay. Well, and if I didn't bore you too much, I guess then that concludes everything for this week. So I guess next week we can cover multiple regressions.
Yeah, in more detail.
Yeah,
Give us more time.
I'll use a data file that maybe has a couple more variables, so we can look at it maybe a more complicated way of looking, a more complicated data file, and maybe even try out some introductions. But if you have something specific that you would like us to also cover, as we did last week, you should also mention that. But yeah, I guess I can stop sharing now.
Okay,
And
I will close the recording.